Okay, the shortcut rules for derivatives, section 2.3. So here we go. Let's see here. It's this button. I always forget. And so these are the shortcuts rules that they give you for finding the derivative. I was trying to figure out my own joke there. Okay, the derivative of a constant. And so this is notation that means find the derivative with respect to x of a constant. And they say that it equals 0. Now when you think about this, y equals 0, let's say, and I'm going to, or 8, and I'm going to graph this. So here's y equals 8. And remember what the derivative finds? It finds the slope. So at every point x, every value of x, the slope is 0, right? The power rule, so this is if you have a polynomial term and you're finding the derivative with respect to x of x raised to the n, then you take this exponent, this is shortcut, down in front, and you take away 1 from the exponent. And this is true if n is, the exponent is any real number. So this will find you the derivative d dx of, let's say, x to the third. And that would be equal to, you move the 3 down in front, 3, and then take away 1 from the exponent, x to the second. If you're wondering why this is, I have the Y video from Khan Academy, and he proves the power rule. And it's just some fancy factoring with the basic derivative of the basic derivative definition. And so anyway, so you can give a try to that. If you're having the derivative of a constant times a function, you can move the constant out in front and then take the derivative of the function so that you multiply later. And this notation right here is the derivative of the function. And so a lot of times students will tell me, well, the derivative of a constant is 0. And so shouldn't this be 0 times whatever have you? And no, it's if you have a constant only, then the derivative is 0. But if you have a constant multiplied by a function, so basically what this is saying is if you have if you're trying to take the derivative of, let's say, 4x to the third, then that 4 can come out in front and hold still while I take the derivative of x to the third, which you guys found the derivative of x to the third was 3x to the second. And so then this would be 12x to the second. And so there we have a good job there. As my husband texted me, will I please shut the door? So I'm going to do that. I guess he wasn't interested in the rules of the rules for finding the derivative. And then the derivative of a sum, you can just take the derivative of the pieces. And so if you're wondering, now what is that saying? So like if I had the derivative of 3x plus 1, that's what I was trying to find. Well, the derivative of 3x is 3, and the derivative of a constant is 0. So so find the derivative of the pieces and then add them together, 3. Okay, so we're going to do some, and so if you're looking at this one and you're saying, why is that? We're going to do that, don't worry, and we're going to do it slowly in just a second. I might not be able to help myself, I might have to go there. Okay, pi squared is a constant, so it's asking us to find the derivative of a constant, so they're trying to trick me here. And so the derivative of a constant is 0. Then this one, I kind of made a conglomerate of a whole bunch of problems in there, and I called it my own example, but this probably was one of the problems, and this was another, and etc., just so that we could look at it all in one example. And I wish I would have put, I did put a subtraction. I wish I would have put more subtraction in there, but anyway. Okay, so when I go to find the derivative here, I want to set this up so that I can find the derivative. So this one's set up okay, so I'm just going to write it. But this one wasn't set up so good. And so I want to pull that apart. You remember that the square root means x means raised to the half. And so the square root of 2x is 2x raised to the half. That's true. I could also think of this as the square root of 2 times the square root of x using square root property, so that this is the square root of 2 times x to the half. And that's actually how I want to think about it right now. So plus the square root of 2 times x raised to the 1/2. In order to use the power rule, your x's have to be in the numerator. So this has to be 3x to the negative 2/3 plus, and I'm going to write this as x to the 1 so that we can use our power rule, because I said I was going to do it slower, right, from that one, minus 4. And now I have all the pieces set up so that I can do the power rule on all of them. I'm going to use the power rule and also the constant multiple rule on all of them. And of course I have a sum and a difference, so I'm going to be using that. And you're going to notice that one of mine is a constant, so I'm going to get 0. So I'm actually going to use all 4 of those rules to find the derivative. So the derivative of f is f prime. And a lot of times students leave that part off. And I know if I looked in the back of the book, they would just say 0 because they asked you to find the derivative. But I think that it is going to be really helpful to you that you don't do that you don't leave that part off, that you write it. I know for sure it's going to be helpful to you, and I know for sure when it's going to be helpful to you, it will be next week. So I am going to make sure that I write that. So I took the derivative of this side, it's f prime. I took the derivative of this side, it was 0. So I took the derivative of this side, it was f prime, and now I'm going to take the derivative of these individual pieces. The constant says that it holds still times, and then I would take the derivative of this as my function, and I can use the power rule. So that's 12 times x to the take away 1 plus the square root of 2 holds still, that's a constant. Then I would take the half, right? So move the half down in front, and I would take away 1. Half take away 1 is negative half. Plus, and then the constant 3 holds still. The negative 2/3 moves down in front. If I write this and don't write parentheses like that, it starts to look like subtract. So you really do need the parentheses there to help yourself. And then I'm doing negative 2/3 take away 1, right? And so I could do that with my calculator or my head. I could say that's negative 2/3 take away 3/3, right? Take away 1, 3/3 is, and so this is negative 5/3. And then I'm going to do there's no constant multiple here, but the 1 comes down in front, plus 1. And then you take away 1. 1 take away 1 is 0. X to the 0, right? And then the derivative of a constant is 0, so minus 0. And then I'm going to clean it up. So I know a lot of you could have cleaned it up as you went, all in your head, but I wrote it like that so that you could see that I just used those rules. And now I am going to do a little cleaning up. Like when I multiply these together, I get 10, right? Because the 6 goes into 12 2 times, and 2 times 5 is 10. So my derivative is 10x to the 11. And then this is the square root of 2 over 2. And then I can put that down in the denominator, right? And so this is the square root of 2 over 2. And then the x to the half can go down in the denominator. And since it started off with square root, I think I'll write it with a square root. So this is the square root of 2 over 2 square root of x. And we're going to talk about that. So leaving it as negative half, sometimes they do that in your book as well, but we're going to talk about this. So I'm coming back on it. The 3 cancels, and I get plus, oh, was it negative? Yes, it was. Minus 2. And then the 3's reduced out, and then I'm going to write this with positive exponents, so 5 to the 3rd in the denominator. 5 to the 3rd? What am I saying? 5/3, x to the 5/3. And then x to the 0, I don't know if you guys remember, but x to the 0 is equal to 1 back in my algebra days, right? So this is 1 times 1, which is 1, and then minus 0. So if you were wondering about me quickly doing the derivative here, well, what did I have as my exponent? I had 1. And so the 1 came down in front and multiplied with the 3, and then x to the 0, which is 1. So that's how that became just 3. Now, having a square root in the denominator, some people are like, oh, you shouldn't leave a square root in the denominator. So you can fix that by multiplying top and bottom by the square root of x there. And then I'm going to call this problem done. And I overdid this problem for sure. I like to overdo things. So this is 2x, square root of 2x, and then this is x, so this is 2x without the square root, minus 2, and then x to the 5/3. My 5/3 started looking pretty 6/30, and you might be like, whoa, why didn't you reduce it? So now it looks better, plus 1. Okay, so there's my answer, and I put it in that simplified form. And so it's very beautiful. Tried to put things with positive exponent the way they had. Tried to make it with a square root, and I rationalized the denominator the way they had and whatnot. Okay, so some more problems to do. Find the derivative, and they're having us find the derivative of j with respect to v. And I've written it in function notation here, and I don't know why they used j and v, but they did. And they gave this. And I just want you to notice that there isn't a rule right now that says how to find the derivative if you have the product of two functions, the multiplication of two functions. There's if you have the addition of two functions. And so since I have a product here, the only way for me to find the derivative right now is to multiply that together. And in the next section, not very long, I'm going to show you a rule for finding the product, for finding the derivative of a product, but I'm going to tell you that multiplying it together is the best way. And so if it's possible to multiply together before finding the derivative, that's what you should do. So here, so even if you've had calculus and you know the product rule, I still think it's better to multiply. Now remember that when you multiply things with the same base, my base here is v, but I'm going to write out the rule like they do in my algebra class. They have the base x or the base b. I guess in my algebra class, the current book we're using uses b. So if I want to really convince you, I would use b. And so the base stays the same, and you add the exponents, m plus n. And so in our case, the base stays the same, v, and we're adding the exponents, 3 plus negative 4, which is negative 1. And then I'll multiply here, plus, and then the base stays the same. You add the exponents, 3 plus negative 2, 1. And the inside, minus 2, and then v, right, v to the 1 times v to the negative 4, right, there's the 2 hanging out there, but I already got the 2 down here. When I add those exponents, I get v to the negative 3. And then last but not least here, minus 2, and then we got v to the 1 and v to the negative 2, so we're going to have v to the negative 1. And I notice, oh, I have some like terms here, so I can combine those like terms. So this is, if I like, and I think I will. So this is 1 minus 2 is negative 1. So this is negative 1 v to the negative 1. And of course I don't have to write this 1 right here, but I do need to write that 1. Plus v to the 1, I don't have to write that 1, minus 2v to the negative 3. Okay, now I can find the derivative. So I'm going to take the derivative of this. So the derivative is j prime of v. I'm going to take the derivative of this, which is now just the constant multiple rule. So the constant stays solid. And the power rule, you move the exponent down in front, -1, you take away 1, so I have -1, you take away 1, that's -2, right? That's my thought, v to the -2. Plus, you move the 1 down in front, you get v to the 0, which is the same as 1. The -2 stays still, right? Constant multiple rule. You move the -3 down in front, better use parentheses, otherwise it'll start looking like a subtraction, and you take away 1. -3 take away 1 is -4. And then now I'm going to clean it up, and yes, I realize that there's many of you can do that in your head, and all of you will be able to do it in your head before it's said and done. So here I get 1, which you wouldn't have to write 1 if it's your coefficient, so v to the -2. This is just 1 plus 1, and then this is +6, v to the -4. And I'm going to leave my answer there with negative exponent because they started off with something that had negative exponent in it. And so I'm okay with that because they started off with the negative exponents. If I wanted to write positive exponents, I could. And so I might look in the back of the book. So I'll put this as a might. I'm going to quote Mr. Serpa. Mr. Serpa says that what you should do when you're doing the homework is you should look at the answer that the textbook gave and see if you can work your algebra to it. And so they might have done this, and sometimes they do, and v to the second, 1 over v to the second, plus 1, plus 6 over v to the fourth, and then that is a good answer. But they might do this, just so you know, they might get a common denominator, which is v to the fourth, right? So they would say this is 1 over v to the second times v to the second times v to the second plus 1 times v to the fourth over v to the fourth plus 6 v to the fourth. I already have v to the fourth in the denominator, so that when the dust clears here, I'm going to have v to the second in the numerator plus v to the fourth plus 6 all divided by v to the fourth. So you might see that as the answer as well. So just a warning on that. Okay, this is problem 22. And problem 22 has this division in it. And you notice that there was not a rule, right now anyway, for how to find the derivative of a division where you have a polynomial in the numerator and a polynomial in the denominator. There's one for if you are adding two polynomials together, if you're adding two things together, they don't have to be polynomials, but subtracting, yeah, there's a rule. There's not a rule for multiplying, and there's not a rule for division, but there is going to be a rule for multiplication and division. And after you get the rule, I'm going to tell you, it's still best to just reduce first if you can. So since I have a monomial in the denominator, I can divide this by dividing the pieces. So d of t here, and so this will be, do you guys agree with me that 4 to the third 64, so this is 64t to the third, so I don't have to write this in a step. 1 over 64t to the third plus 16t to the second over 64t to the third. So I'm dividing out the pieces, right? And so I want to write it so that my variable is in the numerator. And now that this is a monomial divided by a monomial, I can do that. The t to the negative third. So this is a fraction, 1 over 64 times t to the negative third. And that's what I mean by calculus is not too hard. The calculus part is moving the 3 down in front and subtracting 1 from the exponent, right? That's a shortcut on the calculus. But doing the algebra is the part that people get stuck on. And so this is the kind of thing that my beginning algebra students will be practicing. They're not practicing it yet, but they will be practicing it very soon. Let's see here. I wrote 2 here when it was a 3. And you say, why did you do that? And the answer is, I don't know why. Okay, 16 and over 64. I think, does 16 go evenly into 64? I kind of think it does. It goes 4 times. So this is 1/4 And then I want to write this. This is t to the negative 1. I haven't found the derivative yet, but now I am going to find the derivative. And now I have converted this problem from a division into something that's just going to be the constant multiple rule and the power rule, right? So I'm going to take the derivative of this, which is d prime at t. You hold the constant still, 1 over 64, times, you move the exponent down in front, power rule, right? And then you take away 1 from the exponent. So negative 3 take away 1 is negative 4. Plus the 1/4 holds still, and you take the negative 1 down in front, and then you take away 1 from the exponent, that's negative 2. And then now all I have to do is fix it up and make it look better, make it look maybe like it looked before. So d prime at t equals, so this is going to be negative 3 over 64. And I could write this t to the 4th in the bottom, right? T to the negative 4th, t to the 4th in the bottom, plus, and then I realize it's minus. Let's see, 1/4, and then t to the 2nd. And that's a good answer. Probably, though, in the back of the book, because it started off as being 1 fraction like this, they probably write it as 1 fraction. So I always try to match the back of the book because Mr. Serpa said that it would be good for my algebra to do that. So I'm going to have to multiply here, top and bottom. Let's see, 16 times 4, right? 16 times 4 is 64, yeah. So I'm going to be multiplying here, top and bottom, by 16t to the 2nd. And then I'll put it together. So d prime at t equals negative 3 over 64 t to the 4th minus 1 times 16 t to the 2nd, and then 64 t to the 4th. So I'm going to have d prime at t equals negative 3 minus 16 t to the 2nd over 64 t to the 4th. And that's likely the answer that they have in the back of the book. So we did a lovely job on that. Sometimes they get crazy and they factor, and so they might have done that on here, and so I want to show you that. So this is definitely an or. You could have factored out a negative from the numerator there, 3 plus 16t to the 2nd over 64 t to the 4th. And then in algebra class, you learned that minus a over b is the same as negative a over b. So now I have essentially the minus a. This is the whole thing here. And so I bet you that the real answer that I find in the back of the book is this. If I had a dime for every time that someone sent me an email, that's a 16, saying that this is the answer I have. This is the answer they have in the back of the book. I think the back of the book must have made a mistake. But if I had a dime for every time the person's answer was equivalent, when they think that the other person must have made a mistake or the back of the book made a mistake, I'd be rich, rich, rich. And it's our algebra that we have to keep working on. And so the thing I harp on, and so someone said that I shouldn't say that everyone's algebra is bad. And I don't say that anyone's algebra is bad. I say that algebra is a stumbling block for lots of calculus students. And for me as a calculus student, when I was a student, it was a huge block. And helping someone in algebra was what made me be successful. So I should have paid them, is my story on that. Okay, instead of them paying me, definitely. And then this is derivatives and motion. And suppose an object moves along a line, a straight line, with position s equals f at t. The velocity then, remember the velocity was a rate of change, right? And the derivative is a rate of change. And so the velocity is s prime equals, and that's this, and you take the derivative here, take the derivative there, right? And that now is the velocity. So when someone says s prime, that's the velocity. if this is the position that you have. So the velocity is the rate at which the position of an object changes over time. And then the acceleration is the rate at which the velocity of an object changes over time. And so the acceleration is the derivative of the velocity, which is the second derivative of the position. And then one last thing, and that's what's called the jerk. And so here's this funny T-shirt, right, talking about the jerk, and so the jerk is the derivative of the acceleration. Acceleration is, this is a typo. Jerk is the rate at which the acceleration. I had some typos there that I haven't noticed. Okay. Jerk, sorry, my phone was ringing. I tried to turn it off. But it wasn't my husband. He's already told me shut the door through text, right? Jerk is the rate at which the acceleration of an object changes over time. And then also note that speed is the absolute value of velocity. And so velocity can be positive or negative. And if you think about a rocket taking off and going up, the velocity as it goes up is positive. And then as if that rocket goes, like we used to shoot these rockets off, like in Cub Scouts, it goes up, and then it stops, comes down, right? And when the velocity as it's coming down is negative. Okay, so, but the speed, if you're talking about the speed, it's the absolute value, it's always positive. But velocity has direction. If it's going up, it's usually positive, and if it's going down, it's usually negative on velocity. Okay, the equation of a particle, focus, my friend. If I put my hand under there, steadies it. My video camera is saying, I'm 25 years old. You expect me to focus. And so for a video camera, that's very old. For a person, it's very young. It says the equation of motion of a particle is given by this, where S is in meters and T is in seconds. Find the velocity, the acceleration, and the jerk as functions of T and use correct units. And so we're gonna do that. And so if I want to find the velocity, remember the velocity is the derivative of S. So if I take the derivative of S here, then I'm going to take the derivative of that side, which would be 3t to the second minus 3 would be the derivative there. Remember, you can put the 1 there and bring the 1 in front, and then t to the 0, right? So it's just 3. And they wanted me to use correct units. And so I want to show you with a picture what these units would be, because you might be feeling like, well, how do I watch those units go around? So I just kind of want to show you with a picture. So I have S and I have T. S and I have T. And T is in seconds, and S was in meters. So those are kind of my units that I got going here. And I have some equation. I don't have to know what it looks like, but something, I don't know what it looks like, but I got it going there, but it doesn't matter. And when you find the derivative, what you found is the slope. And remember, the slope is the y's over the x's, right? In this case, the s's over the t's. So look at S prime is the slope, and that is the y's over the x's, which is meters over second. So that is the units here. And think about it, that makes sense for the units on, that you would have on velocity. Now, another way of looking at it is other notation besides S prime for the derivative. So some people would say that S prime, I'm going to write it over here, is the same in this case as ds dt. And certainly it is. And now you can see the units. S is in meters and T is in seconds. So that works too. Now they asked me to find the acceleration. So the acceleration is the second derivative. And so all you have to do to find the second derivative is to find the derivative of the derivative. So if I want to find the second derivative, take the derivative of this, which would be this, and then take the derivative of this, which would be, the 2 would come down in front, so that'd be 6, right? T to the first, and then a constant. And then I want to show you what the units would be. So on a picture. So here we had velocity, and here we had time. Velocity and time, right? This was in seconds, and this was in, remember, meters per second. So that when you, and you have your function going here, and you're going to find your slope, and it's this over that, right? So it's meters per second over seconds. I guess I've got SEC and S going for my seconds, and so I'll clean it up and have it all be the same. And I just want to show you mathematically how this turns out. This is meters per second divided by, right, seconds over 1, and, multiplied, divided by, and then I wrote multiply, and then you would flip it good, right? And so this is here times 1 over the seconds. And so now you see what you have. Meters times 1 is meters, and seconds times seconds is seconds squared. So this is meters per second squared, and I'm just going to use S, is what it is. And then jerk, it's the last one. And the jerk is the third derivative, which is the derivative of the second derivative, which is 6. And the units on it, and you can kind of do the same story on it. And so if you write the units that you would have going, right, for each of the pieces as you go along, then you're going to find that this is meters per second cubed. Okay, so that's what they asked us to do, and they wanted to make sure that we knew what the units on that would be. And then it said, it asked us to find the acceleration after 2 seconds. And the good news is, all I have to do is use the formula. So A equals 6t after 2 seconds. A equals 6 times 2, lost my units. And so this is A equals 12 meters per second squared. So a lot of times people put the units wrong, and they think they shouldn't get any points taken off for that. So they put meters per second squared, which is not right, or they put meters squared per second, and that's not right as well. And so it is really important. And then they asked me in part B to find the velocity, find the acceleration when the velocity is 0. So the velocity was this. The velocity is 3t squared minus 3. And they wanted us to find the acceleration when the velocity is 0. So I'm going to set the velocity equal to 0 so I can find out when that happens. And so you could add 3 to the other side and then divide by 3. So I get t squared equals 1, right? And so t is truly plus or minus the square root of 1, which is 1. But time shouldn't be negative, so it should just be 1. And so they're really asking me to find the acceleration when the time is 1. So I just found the time is 1. 1 second has happened. So the acceleration is 6t, which is 6 times 1, meters per second squared. So the acceleration is 6 meters per second squared. Okay, so that was that question, problem 64 out of your book. You did a lovely job on it. And then in class, oh, and I wrote on this paper, was up at the top is why that happened. But I have some read more when you get home. And so you can definitely read about acceleration and how it feels, and linear acceleration. They talk about all kinds of things, and being a passenger in the car and what it feels like to have acceleration. And they talk about jerk, and they talk about how engineers spend a lot of time and money getting rid of jerk. Otherwise, you would be sick when you went on a roller coaster, sick when you went on an elevator. Maybe you get sick when you go on a roller coaster. And then a few more rules for finding derivatives. And so this is the product rule. And it says if you're multiplying two functions together with respect to x, that to find the derivative, you find the derivative of the first times the non-derivative of the second plus the derivative of the second times the non-derivative of the first. Whatever order that you like to write that in, it doesn't matter. This is notation with f's and g's. This is notation with prime. This is the notation I actually usually use. UV prime is telling me find the derivative of a product, and it's u v prime v u prime. So one of them without the derivative, the other with the derivative, without the derivative, with the derivative. You notice it's written backwards here, or this appears backwards of that, because it doesn't matter, commutative property of addition, right? And then the quotient rule. So if you have something that looks like this, then you take the derivative of the numerator times the denominator, and minus the derivative of the denominator times the numerator, right, over the denominator squared. And this is the notation with u's and v's. And however you want to have it memorized, or however that you do it is fine and dandy with me. So here they're saying p at x equals f at x times g of x, and they must have a picture down here of f and g, and they do. And they've asked us to find p prime at 2. And so because p is put this in here, because p is a product, I would have to use the product rule, right, to find the derivative of it. And so I could just write it, here's the product rule, and it's almost the same, only capital F and lower capital G, right? And so I'll just write it the same as what we had up there. Times g prime of x. Okay, so there's the derivative, and they said to do it at 2. So this is at 2, at 2, at 2, at 2, at 2, right? So I'm going to do that. And my prime got crazy, and then my 2 got not at all. And then I have to go look up this information, and I have showed like every freaking step, and you're like, do you have to show so many steps? And sometimes it's helpful. And so if it's not helpful, speed me up, right, on YouTube, if you don't need all the steps shown. And if you need more steps, I don't know if you can get more steps by slowing it down, but at least it won't go so fast, right? Okay, remember that this says find the slope, right? Remember, that's what that says. Find the slope of f at 2. So the slope, here I am at 2 on the f graph, the slope is 0. So it doesn't matter what g of 2 is, because 0 times that is going to be 0. But I'm going to go ahead and find it just for the practice of it. So this says, it doesn't say find the slope, it says find the y value is what it says. And the y value is 2. Plus, now it's saying find the y value. So this is the y value is what we're finding here. And using the graph to find the y value. Using the graph to find the y value, this is going to be find the slope, right? So I'm going at 2 and finding the y value, which is here at 3. So the output here is at 3 times. And then g prime at 2 says get here on the g graph and find the slope. And I was taught by Mr. Heater to find the rise over the run when I was finding slope. And Mr. Heater taught me to find the run first, but it does not matter. So if your teacher taught you to find the rise first, then that's fine. So I'm going to walk from this point to that point. In order to find the slope on the line, you just go between any 2 points. And so, and the nicer the points, the better. So I kind of had to get crazy on the last video. So this is over 2, right? Over 2 is my run. And then my rise is up 1. And so half is the slope of that line. You could have done it any which, your choice, right? I would not have picked that point because then I would have had to estimate where it was, and if you have the choice of going exact, you should go exact. So 0 times 2 is 0, and then, so 3/2 is my answer here. So P prime at 2 is 3/2. That's what they asked us to find. So we did a lovely job on that. And now, friends, my calculus doing friends. I remember when I was at Fresno State that one of the things you have to do is take a master's qualifying exam. And the master's qualifying exam is on proving the stuff of calculus. It's on real analysis. The proofs for calculus, I get a little bit more light in here, is a class called Real Analysis, where you prove the product rule, which we're learning, and the quotient rule, and the chain rule, which we're going to learn, and et cetera, et cetera. And the practice they gave out for the test was a bunch of these proofs. So I was really ready for that. And what they asked instead is they asked those proofs too, but they had one question, and it asked us to find the derivative like g prime at 2, given a graph like this. And at first I left it blank because I had been a long time since I had taken calculus. By the time you're getting a master's in math, took calculus at Bakersfield College, as you know, and then took the whole calculus series. So there are a lot of practicing calculus there, and of course calculus comes up in math as you go along, but really complicated looking stuff, not really easy stuff like find the slope. And I don't know why I could not think of what I needed to do. I did finally figure it out, but when I was having lunch with my friends that also had taken the test, the only people told me they left it blank. And at first I had left it blank, and I was grateful that I finally, my uncle Keith, who teaches agriculture at the college, at Bakersfield College, used to, he's now retired, but he always would say, the only thing I remember about calculus is the derivative is the slope at a point, and the integral, which we're going to learn about, is the area under the curve. And I tell you what, he saved me that day with his saying, because the only thing he remembered about calculus was that question, and I was almost leaving it blank. And my friends that were not teaching calculus, because you get into this, all this theoretical stuff, and you get away from the basics, and man, you forget some of the basics. It's embarrassing. Okay, another story. Enough of talking, right? Get going on math. The tangent line and the normal line. And so the tangent line is at a point, it has the same slope as the curve at that point. And the normal line, it intersects the curve, if you have the normal line at that point, and it is perpendicular to the tangent line. So the normal line passes through the point P on the curve and is perpendicular to the line that is tangent to the curve. And why that's helpful is because if you know the slope of the tangent line, if you know that, right, so that's something we've been learning on finding, then the slope of the normal line, and do you guys remember if they're perpendicular from your algebra days? It should be -1 over the slope of the tangent line. They ought to be, they should be negative reciprocals of one another, right? So the slope of the normal line should equal -1 times the slope of the tangent line. And so that's, I don't know if you guys remember finding perpendicular lines when you were in algebra, but that's the story right there, right? Okay, so they have this serpentine, the curve y equals x divided by 1 plus x squared is called a serpentine. Find the equation of the tangent line to this curve at a point 3, And so they're wanting us to find the equation of the tangent line, right? The equation of the tangent line. And so the steps to finding the equation of any line, tangent line or other, is to find the slope of that line and to find a point on that line. And then you use this formula when you're trying to find the equation of the line. And in algebra class, they gave you this, they gave you that, is what they did, and then you found this. And right now, they're giving us the point. There it is, 3.3. The x value is 3, the y value is 0.3. If you put in 3 here for x and do the arithmetic, that would be 3 over 10, and 3 over 10 is 0.3. So they could have just told me the x value, and with the equation, I could have found the y value to that point. But they gave me it both, but I'll just show you that because some of them don't. But they are requiring that I find the slope. And how you find the slope is that you find the, do you guys remember the slope is the, do you guys remember? Yeah, it's the derivative, right? So I need to find the derivative of this. And I notice that it is a division that I can't reduce. It's a monomial over a binomial. And so I can't find that division. And so I am going to have to use the quotient rule. And so to find the slope. So that's here, you know, check mark, I have it, 0.3, right? Check mark. Now this is what I'm going to be finding. That's going to be my work, and then I'll put it in over here. And in order to use the quotient rule, I usually label, and I usually use U and V, and you could use F and G if you wanted, it doesn't matter, U and V, and I usually write U like this, so I have a pattern, I guess is what I'm going to say, and so I usually write my U is X, my U prime is 1, right, and my V is 1 plus X squared, and my V prime is 2x. And remember, I was going to use the quotient rule, right, on this. And so my quotient rule is y equals, and then the quotient rule is, and it doesn't matter how I write this, if I write this v u prime, or if I write it u prime v, either way, right, minus, and then u v prime divided by v squared. And so that's the rule, right? And I have things that I'm going to be plugging in here. So for v, I have 1 plus x squared. And for u prime, I have 1 minus. And then for u, I have x. And for v prime, I have 2x. And then over v squared, so this is v, so 1 plus x squared squared. And then I need to clean that up, right? And so I certainly can clean that up. I'm going to show you another way of doing it, and they're both good. And so here I am. This is a lot of algebra approach, and then I'm going to show you not so much algebra approach. So 1 plus x squared, this is still equal to y prime, minus 2x squared over 1 plus x squared squared, and cleaned up, this is 1 minus x squared over 1 plus x squared. And then they asked me to find the slope when x is equal to 3. So that's the next thing I'm going to do, is I'm going to find the slope, right, which is y prime. This is the slope of the tangent line, which is y prime, and that's going to be 1 take away 9, 1 minus 3 squared, right, 1 plus 3 squared squared. And so let's see, 1 take away 9 is negative 8, over 1 plus 3 squared is 9, that's 10, 10 squared is 100. And 8 over 100, that does reduce. 2 over 25. So this is negative 2 over 25. And that's cool. We did a lovely job on that. And I did all the algebra and whatnot. And I can't help but showing you a shortcut. And I have to also tell you that I don't have my derivative for a quotient rule memorized by the quotient rule. I have it memorized by a pattern. And you can memorize, when you have formulas to memorize, you can memorize them any way you want. So I memorize the difference of cubes, factoring the difference of cubes with a song, and you can memorize it with a formula. Thomas Mee, who is a math teacher who I love dearly, always says, "Why are you always singing that song? Why don't you just use the formula?" And then I'm going to tell you something right now of how I would find the derivative here. And so this is probably what a lot of people would show, doing a lot of the work in their head. But I'm going to show you what I would do to find the derivative here. And my office mate, Arnie Andrazian, who I love dearly as well, would say, you're going to use he's going to call it my kindergartner approach, being funny because it's not, I don't know that very many kindergartners could do this. But anyway, the slope of the tangent line. So remember, I've already found all the derivatives that I need to find, right, when I wrote this out. And so it's okay for me to evaluate this at x equals 3, right? That's what my x was. So u is 3, u prime is 1, 3 squared. You can only do this after you found the derivative. So I have found the derivative. I just haven't stuffed them into the formula yet. So 3 squared is 9 plus 1 is 10. And 3 times 2 is 6, right? And then what I say, this is what gives the kindergarten approach. I say crisscross applesauce, because I'm going to multiply those together. 1 times 10, and see how they're across from one another, minus, and then I'm going to multiply these together, minus 3 times 6. And I would usually not write the 1 times 10 and the 3 times 6. I would usually do that in my head over 10 squared, which is 100, right? And so you can kind of see how I would go. This is normally what I would write, would be 10 minus 18 over 100, which is negative 8 over 100, which is certainly negative 2 over 25, the same thing that we got there. And so that's my approach to it. And they're both right. Neither one of them is more right than the other. They're both good. And so the only thing that can kind of mess students up sometimes is plugging in too early. Because if you plug in numbers, then you have constants. And then when you take the derivative of a constant, you always get 0. And so you have to make sure that you found all the derivatives that you're going to take. Now I haven't left, by doing it twice here, I haven't left very much room for me to find the equation of the tangent line. But now I do know the slope, right? I needed to know the slope, and I needed to know the point, and I'm plugging it into that formula right there. So that's what I'm going to do now. So y minus 0.3 times the slope, which is negative 2 over 25, times x minus 3. And so long story short, you should solve for y. So this is negative 2 over 25, x plus, and let's see, that's going to be 6 over 25. And I'm going to add 0.3 to that. And I don't even think I will even worry about using my head to do that. I think I will use my calculator to do that. A lot of schools in their calculus program have gone to no calculator. And I know that UCLA has actually gone in their math program to no calculator at all. And so my son right now is coincidentally at UCLA, so I know this for sure. And he's almost done. He's almost graduated with a degree in math, and in applied math even, and has never used a calculator in any class at UCLA, not allowed to use a calculator in any class at UCLA. And it's because they want to know if you can do basic things in your head. We are at Bakersfield College. We don't use a I got decimals and fraction in the same equation, so I'm going to write this as a fraction so that I don't feel silly. So it's 27 over 50. I feel happier now. We don't allow graphing calculator on exams. And so you can use graphing calculator to learn how to do things or whatever have you. But a graphing calculator will shortcut out a lot of the thought process that they're wanting you to have. And so that's the reason. And so at UCLA, if you were taking calculus, you wouldn't be allowed to use a scientific calculator, but I allow you to use a scientific calculator. And I think most of my colleagues do too. And the moment they don't, I guess I'll have to change my mind. Find the equation of the normal line. So they're asking for the equation of the normal line. And so what I need to know is the slope, and I need to know the point. And well, they already gave me the point. It was at the point 3, 0.3, right? And actually, I can find the slope because I know the slope of the normal line. Slope of the normal line is equal to -1 times the slope of the tangent line. And so that's -1 over, and then what I have was -2 over 25. Flip-flop, right? So this is 25 over 2. And some people say, well, instead of doing this, I learned the shortcut that you take the opposite. So negative, you take the opposite, so it's positive, and you write it as a fraction and flip it, which it's already written as a fraction, and you flip it. So you can see that that works. So now we know our slope, and so we're happy, right? I didn't have to do additional work. I already had really basically the slope, and I'm going to find the equation of the normal line. So the equation of the normal line is y minus y1 equals m times x minus x1, no new formula, y minus 0.3 equals 25 over 2 times x minus 3. So y minus 0.3 equals 25 over 2x minus 75 over 2, and then I'm going to add 0.3 to that. And like I say, I'm going to use my calculator. So y equals 25 over 2, and I'll write this as a fraction. So what do I have? -75 over 2 plus 0.3, and that's -186 over 5. Okay, so we did a lovely job at finding the equation of the normal line. A really common boo-boo that I see a lot is people will think that they can come right here and just change the slope. And you notice that wouldn't have worked, right? And so you can't do that. So anyway, so that's the story there. And then they wanted me to illustrate part A by graphing the curve, the tangent line, the normal line on the same screen. And so I've given you from Desmos this, and I'm going to graph the tangent line. So we're here at 3. And so right here, I'm going to draw the tangent line in there. Now my tangent line was y equals -2 over 25x plus 27 over 50. And I know that point, when I put it, if I put in 3 right here, oh, I'm off the screen, sorry. If I put in 3 right here, this is my tangent line, right? Tangent line. Lost it in tangent there. But if I put in 3, without doing the arithmetic, do you guys know what I should get? Yeah, it should be 0.3. It should be that same point. So I'm going to do that just to verify. If you don't have your calculator out and you're not verifying as well, then I think you're missing the boat, and I think that you should. So I got 3/10, which is 0.3. Okay. So I have that plotted right there. Now I want to get another point on the curve just so that I can graph it. So I could pick like x is 2 if I wanted, or x is 0 if I wanted. whatever. Maybe I'll pick 0. What the heck? So that's 27 over 50. And that is equal to 27 over 50, just to help me put it on there, is equal to 0.54. So here's 1, and 0.54 is just a smidgen bigger than half. So 0 there. And I'm going to draw on here with my BC math ruler. I know, that's so cool, right? That I have a ruler that has BC math on it. It makes me so happy. And so there is my tangent line. And you can see that the tangent line looks like, if I was to zoom in on that point, that the curve and the tangent line are exactly the same. Now, as I get away from 3, then the tangent line deviates from the curve. But the tangent line is mocking the curve at in that little neighborhood right there, right? And now I want to graph on the same graph the normal line. And the equation we have for the normal line was 25 over 2x minus 186 over 5. And if I pick a point, 3, do you guys know what I should get from my y value? Yeah, I ought to get 0.3. And if I don't, then there's a mistake. I made a mistake somewhere. So I'm going to make sure that I do get 0.3 here, and minus 186 over 5. And I do, right? 3/10. It's 0.3. So hot diggity dog means I haven't got a boo-boo going yet. And so this normal line, when I think about what point I'm going to choose, like the tangent line, it was pretty easy. Anything I picked would have been good, and just good enough to make a sketch of it. But if I want to stay on this grid, I have to be really careful about what I pick. And I think even 2.5 gets right off the grid. And so I'm going to just show you that. I've learned this from doing this problem before. So like if you're like, well, how did you know that that got off? Well, you could kind of eyeball it. But negative, so that's negative 5.95. And so you can see that it's off the grid that I have. So I really need to get closer, and so closer to 3. And so this is, if the grid I had was better, or if the grid I had went down there, I could certainly plot that and then have 2 points and draw it. But I'm going to pick 3.1. And that's what that's going to do for me. It's going to be on the other side of my line, so it's going to be where I have more room. And then I'll plot that point. So that's 1.55. So 3.1, this is 3.5, so 3.1 is somewhere here, and 1.55. So this is 1.5, right, the height for it, so 155 is somewhere right in there. Of course, my dot's so big. And then you can see that when I draw this in here, that the tangent line and the normal line are meeting perpendicular with one another, right? They're meeting square. And so here's the normal line. And that's all that they wanted me to do, because they were just wanting me to verify how, what I found, right? So at the point 3.3, we knew that should be on there, etc. Okay, so we did a lovely job on that. And I have one more example, and then I'm going to get some lunch. Lunch. I'm really excited about it too. I'm always talking about food. I think food's like my favorite thing. Biologists have proposed a cubic polynomial to model the length of Alaskan rockfish at the age of A. And so I have read and whatnot about rockfish. And so I like rockfish. I think they're kind of cool. And that they almost went extinct. And by biologists studying them and then putting in measures, those crazy hummingbirds have eaten all the food. Those hummingbirds are pigs. There was 6 eating at one time, and one more came, and it was 7. Just for a brief moment, it was 7 of them. I can't believe. And you can almost see the you know, my cat's going crazy again over them. But anyway, they, by studying the rockfish and putting in place things, they've come back, and now there's something that you can even, you know, they're even put on the they're sustainable. How do you say that word? I can't get it. And of course, students would help me. I am very bad. I'm sorry. So they're okie dokie to eat, right? And so anyway, so they're asking me, they say they got this cubic polynomial to model the length of the rockfish, and they want us to find DLDA, and so at 12. A is 12. And then they want me to interpret my answer. And so finding DLDA is going to be not so hard. This is notation for finding the, you guessed it, the derivative. It's like everything is notation for finding the derivative. They could have also said, besides DLDA, they could have said L prime. That would have been another thing that they could have said here. And so I have plumb run my pencil out of lead. Can you believe that? That's crazy. So anyway, so we're going to find the derivative. So we, this holds still and the 3 comes down in front. So DLDA. So find the derivative of this. It's DLDA. I was going to write L prime, right, when I ran out of lead. And then, so this is going to be 0.0155 times 3a to the second minus, and then 0.372, that just holds still, the constant, times 2a to the first, right? Plus 3.95, the 1 comes down in front, right? The 1 comes down in front, a to the 0 is 1, so times 1, and then the derivative of a constant is 0. And so DLDA, when I fix it up, multiplying these together right there, right? And I plan on using my calculator to multiply those together. 93 over 2,000, or 0.0465 a squared, minus, and then 2 times, and I forgot my decimal point, 0.372 is 93 over 0.2. So finding the derivative happens in a lot of disciplines besides just math. So this is an example of just basically finding a derivative in a easy to find derivative in biology. My brother was an economics major, and he said that that you find the derivative all the time in economics, and they call it all these fancy names, he says, and he says, you know, it's just the derivative. And anyway, so we're going to put in 12 here and then do the arithmetic. They put this straight up and down line, and all it means is I'm going to evaluate this at a is 12. Is what that it means, and it's really common mathematically to write that. They'll even put just 12 there. You'll see, so if you see that in your book or whatever, and you're like, what the heck? And that's all it means, is that I'm going to evaluate this at 12. And so squared, putting it in my calculator. I hope you're putting it in your calculator right now as well. So I'm getting, having too much, huh? Too much caffeine. So DLDA. So a lot of times it helps just to even have the units on something when they say to interpret your answer. So L was the length, and it was measured in inches, and A was the years. So this is inches per year. so inches per year. And this was modeling the length of this rockfish. If I draw a fish, will you guys laugh at me? If I draw a fish, right? So there's my rockfish. Of course, my rockfish is a rock star, so it will be smiling for sure. And so you guys are probably not getting that rock star, right? And so that's the kind of rock star I would be interested in. And so there's my fish, and if I'm talking about its length, do you guys agree that this is like a growth rate of my fish when the fish is 12 years old? So this is the growth rate, or the change in length of the rockfish when 12 years old. So we know in humans that there's different times that your growth rate changes. It's not constant, right? And so like when you're a baby, and you're this big, you grow really, really fast. But there's time, like right now, I don't think I've changed in height in years. And so my growth rate for my height, I'm not going to talk about my growth rate for my circumference, but my growth rate for my height is probably 0 or very near 0. Anyway, so that's kind of the story on this problem here. And one more video to make for this week. Hot diggity dog.